Hello, I'm glad we have another opportunity to talk about big things. Last time it was big earthquakes. Next time it'll be big wildfires, mega fires, gigafires. But this time it'll be big floods. And floods aren't really what you think about when you think of San Diego, but they have happened and they will happen again. And what we're kind of looking at here is the world is changing, as you know. Things are getting warmer, the atmosphere is warmer, the oceans are warmer. We've had 50 years of warning about this from very good computer models. The models from 50 years ago had turned out to be Nobel Prize winning good. And what we want to do now then is, with this world that we understand better and better, think, well, what might happen in San Diego given a chance? Now, what we see here is a billion-dollar weather events. Now, this is 41 years here, 1980 to 2021. And I might add that the dollars have been evened out for inflation, so the dollar amounts are all equivalent here. And one of the things that we've talked about with the warming world that the computer models told us 50 years ago is the warming, the changing of the climate would be accompanied by more frequent severe weather events. And if we start over here and you look at the left side of the diagram, lower left here, that's 0 events per year, and we had 0 in 1987, for example, and over here is 16 events, billion-dollar events a year. And what we have here, then you can easily see that difference, and I didn't do this arithmetically to plot the line, but I just dropped a red line on there to kind of show that what are we seeing? We're seeing that these severe weather events are becoming much more frequent. Look at that change through time, as had been predicted. Now, along with this, then we want to think about, well, what things like this might come and affect San Diego. And here we're going to look at the oceans. Now, over 90% of the excess heat that's been generated by humans has been absorbed by the oceans. Now, in this particular plot here, this is 67 years. We're going from the lower left there, 1955, all the way up through 2020. And what they did was average out the temperature over that whole time and then go back to each 3-month period of each year and figure out how close they were to the average. And what you clearly see when you look at this is it's more and more heat being stored within the oceans. When we start at the left-hand side of the diagram and look over there and we see so many of them less than the average. There's one red one peaking up. These are 3-month intervals. That'd be one real warm summer, presumably. Then we go in the middle. We kind of go into a transition time where it's warm summers, colder winters, and so forth. But now we get to, from 1995 on, what do we see? Just massive, overwhelming amounts of heat being stored in the oceans. And of course, the significance of this is the more heat that's stored in the oceans, the more moisture there is to release to the atmosphere, the more energy we can generate or build up the conditions that could lead to large storms. Now, here we're looking at another view of the ocean heat buildup. Now, lower left, you see we're going back there to 1993, going over to 2019, and this time what we're doing is we're looking at the heat content compared to the depth of the ocean. So when you look at the upper parts there, the red, yellow, orange, those are the surface waters down to about 2,300 feet deep, and that's where most of the warmth has been. Drop down one level where it's greens and blues, we're going down to a greater depth from 2,300 feet to more than 6,000 feet. And then down at the bottom, the gray wedge, we're looking at even warming down here in the deepest parts of the ocean. Now, as you know, the ocean moves. There are currents, there are tides, that the water within the oceans does a complete circuit every maybe 1,600 years or so. So this heat that's in the surface water now, a lot of that heat's going to be stirred and mixed in the oceans. In other words, we're part of a long-term heating up of the oceans. Now, these are these global measurements that show us what's going on, but how do we experience it? What are the kinds of things we see right now? And one of these, heat waves, always had heat waves. This San Diego, we got a Santa Ana, we're going to have 100-degree days. It's a heat wave. Well, we also see this heat build up in the oceans now. We see things like these marine heat waves. Here's one here that they call the blob, where so much heat accumulated in the oceans, didn't have storms to stir up the water and mix up that heat, but you allowed the water to get hotter and hotter, and then that means greater potential for some kinds of storms. Now, what I want to do here with these marine heat waves, which are occurring in other oceans around the world at unpredictable times and unpredictable places, the main point is there's more energy, more moisture available for storms. I'd like to go on to one here that's kind of familiar to us, and that is the El Niños. And what I'd like to do here is, first I'd like to start with the northern hemisphere here. The southeast trade winds push the water across the ocean, from cold on our side to warm on the other side. And in the southern hemisphere, the southeast trade winds push the warm water over here up against, well, the Great Barrier Reef of Australia. And if we look at that now in a depth perspective, what we'll see here is, here we are, Peru, the Americas. The water there, that warm water, is thicker, deeper. And for that matter, that term sea level doesn't even apply. The sea is not level. There not only is more warm water on the Australian, Indonesian side of the Pacific Ocean, but the water level's higher. So then what happens then when those trade winds relax? Then what happens is, now we see the warm water comes flowing back against the Americas, and this is our El Niño. Every 2 to 7 years we get an El Niño. They last for several months, maybe even as long as 2 years. And there are times that are really marked that we can remember, like 1982, 83, 1997, 98, 2014 to 2016. Some of those ones are very, very intense. Not all El Niños have the same amount of warming, but the really big ones have big effects. So what I've been doing here so far is we've seen the oceans are warming. We've seen marine heat waves occurring. We have the El Niño, which we're familiar with. And let's see what are some of the things that could occur from all of this. Now, on this El Niño here, you're looking at 1997, and look at that. Look at how much of that hot water, colored here in white, has flowed back over the equator against the Americas, and then flows on up the coast. Look here off of Baja California, California. Look how much heat we have in the water right there. These are times where big things can happen. Now, did you know this? San Diego was hit by a Category 1 hurricane back in 1858. Now, we don't have satellites to tell us about El Niños then, but we are able to read things out of corals about water temperatures. Coral put on annual growth rings, if you will, growth layers, and we can look at the isotopes in those, and we can tell you that the year 1858 was very warm ocean water, and warm enough here for San Diego that a Category 1 hurricane, oh, and by the way, I should mention, I put in a photo of Hurricane Katrina. The satellites weren't working so good back in 1858, so I put one in so we can see the big counterclockwise rotating tropical cyclone. But the hurricane, it was a Category 1, but 80-mile-an-hour wind speeds, did not make landfall, but you know that doesn't really matter. As long as it runs along the coast, you see that big spinning circle there, that big, huge rotating vortex. You don't have to have landfall. Imagine you're on the right side of that picture right there. Look at all those bands of clouds coming in. So 80-mile-an-hour winds hit San Diego. Population of San Diego then is about 4,300 people, but it lifts the roofs off of houses, knocks down the trees, takes the boats, ships, pushes them ashore, tears apart the fences. It did a lot of damage. Somebody tried to calculate what that same storm would do to San Diego today in terms of damages, and they come up with a number like 500 million. So in other words, this storm was a big deal. But that's 1858. So let's look a little bit more here at the oceans. What I'm trying to do now is to start to set up something about how likely are we to have hurricanes coming to San Diego? How much has the odds increased that such a thing would happen? Now, what we want to see here first over in let's just look at the Atlantic Ocean here first, the North Atlantic. Let's just talk about the northern hemisphere. See that clockwise rotation there, where down the trade winds pushing the warm water over from Africa, also bringing African storms that can grow to hurricane strength and then hit the United States. But We don't have that in the Pacific Ocean. What happens to the circle, that is to say the rotating water in the Pacific Ocean? The warm water is going up the east side, and what's coming back down the Americas here? There's the blue arrow. What do we have? We have that cold water. Well, let's talk about what does it take to make a hurricane. Well, we want the ocean water temperature to be at least 80 degrees Fahrenheit. We'd like to have the air moist. We'd like to have it unstable. And we don't want upper level winds, any other winds to come in and interfere with things. So for San Diego, anytime a hurricane starts to come towards us, it gets the energy sucked out of it by the cold ocean water from us. But back to what we've been looking at, marine heat waves, El Niños, there are times when the water is warmer and the oceans as a whole are getting warmer. So does that increase the odds that more hurricanes like 1858 might come up to us? Here's a global view of, we call them hurricanes, as you see there in the middle, but over on the left side, in the western Pacific Ocean off of Asia, they call them typhoons. And if we go all the way over to the Indian Ocean, they call them cyclones. They're identical storms. They're all tropical cyclones. We use the word hurricanes. What I want you to look at here is the North Atlantic Ocean. Hurricanes there, 12%. What we're talking about here is on average, for typical years, the Atlantic there, the North Atlantic, would have 12% of the world's hurricanes. But look at this little surprise thing. Look right over here. What do we see? 15% off of Mexico, Central America. Look at the coastline. See how the coastline jogs in there? And that's called the East Pacific Warm Pool. So we have there, in that little armpit, if you will, of the Americas, we have a lot of very hot water, and then we have a lot of hurricanes formed from there. But what happens to most of those? Very impressive plot. Kind of thing I'd like to cut out, frame, and hang on my wall. But what we're looking at here are the tracks of hurricanes from 1851 up to the present. Now, when you look at these colored lines, each one is the track of a hurricane. And for their intensity, the purple and red is the most intense, then orange, then yellow, then green, then blue. And what do we see when we look over here on the right-hand side into the Atlantic? What do we see? These storms are pushed over by the trade winds. They grow in strength, and then the Coriolis effect comes into play, and they tend to hook and go to the right, go clockwise, and some of them go all the way over and hit the United Kingdom, for example. What happens to us over here where we're affected by the East Pacific tropical warm spot? Look how many initiate there. You notice that where each one of the lines, each one of the hurricane tracks begin, they're blue, they're just tropical storms in, and then they grow in intensity. They get green, yellow, orange, red, and then as they start coming up towards us, see how the colors change. The hot colors go away, and we see the life, the energy being sucked out of the hurricanes, and then most of them disappear and don't hit us. But there are a few that have. We've just mentioned a little bit about the San Diego hurricane in 1858 that passed along offshore. And I might also mention about hurricanes passing offshore. How big a deal is that? 2016, off of the Atlantic coast, Hurricane Matthew never made landfall, but it went alongside Florida, Georgia, South Carolina, North Carolina, and did $18 billion worth of damage without coming ashore. It sent enough winds ashore, enough big waves to create damages galore. Now, the only tropical storm or hurricane that's made landfall is 1939, one that hit there in Long Beach. That hit at about 50 miles an hour, the wind speed then. 74 miles an hour is the cutoff lines between hurricanes. That's when the eye develops in the center of the swirling vortex. And then below that, we go to tropical storm. But lots of rainfall there, estimates of up to 93 people killed, mostly people in boats that are offshore, that were driven ashore, and marine incidents. And another one, the closest San Diego's been in recent times, you see that there, Tropical Storm Kathleen in 1976. Kathleen dumped 10 inches of rain on the Laguna Mountains, which then flowed out into the deserts. About 10 people were killed. Did serious damage to Interstate 8, knocked out the freeway bridges there. where you drop from Jacumba down to the desert floor. There's the big heavy cement bridges. They were knocked out. I-8 was out of action for some time. The San Diego and Arizona Eastern Railway was knocked out by Kathleen and has never reopened. They never recovered from that damage, and don't have a really good picture of all the damage that took place. But here's a Weather Service image of the rainfall of Kathleen. You look at that track. See, Kathleen crossed over the northern Baja California Peninsula. That Coriolis effect, that clockwise curve that those moving storms make. So it came in on the east side of the mountains, but you see those deep orange, that's the rainfall of the mountains flowing to the east. Well, that can come up with a slight difference in that hook. It could have hit on the slopes facing west, and all that water could have run down through San Diego. So I'm going to say 1976, for the residents of the city of San Diego, that was a near miss. The folks that took the hit were out here. This is the town of Ocotillo, the town you get through at the bottom of Interstate 8 when you hit the desert floor. Pretty well wiped out right there. We're not seeing the people that were killed or houses that were totally destroyed there, but you get the feel of the massive floodwaters that flowed through there. So take a little bit more of a close-up here now of the hurricanes we were looking at. And what I want to do here now is follow some of these tracks up and think, what are we doing now with marine heat waves, with an El Nino, with things of this sort? Some of these tracks, look how many these tracks end right there. Well, if we have warmer seawater, those tracks aren't going to end. If we can get energy out of the water, if the water's warm enough that the hurricanes, tropical storms can still suck up energy out of the water, then they would have enough strength to go on and hit into Southern California. Now, I'm not being a meteorologist giving you the weather forecast for tomorrow or anything like that. I'm not even saying when's going to happen immediately, but I'm just saying that the odds of hurricanes coming in are increased as the oceans continue to warm. Here is one that was really exciting there for some time. This beautiful picture right here, this is Linda. Linda, and you see there in that swirling vortex, 185-mile-an-hour winds, the fastest wind speeds that ever had been measured in an East Pacific hurricane. Side note, in 2015, Hurricane Patricia exceeded that, but this is still the fastest one ever. And when we think about that, here's Linda heading on this hook up towards Southern California. And look at the waters here. What kind of waters is Linda going to run into, or did Linda run into? This is 1997. This is right during that El Nino, which means we had Linda here, but as Linda comes hooking up this way, look at all the warm water waiting right there. So we were emailing back and forth and calling and talking and thinking, my goodness, are we going to get hit or what? Here's the official National Weather Service prediction of the path. The path, look at that, they have Linda coming up and into Southern California. Now, Linda wouldn't have come in with the 185-mile-an-hour winds. The waters weren't warm enough to keep feeding a lot of energy in, but they were warm enough that you don't suck as much energy out. So even if you get hit with wind gusts, as they predict they're 65 knots, that'd be more like 80 miles an hour. 80 miles an hour, then all that rain, moisture that Linda was carrying, that would have been one heck of an event. That's 1997. So Kathleen in 1976, Linda in 1997. We're not talking about totally remote possibilities here. Something just may happen, and we may get to experience that. Here's the actual path of Linda. A high pressure zone came in from the north and then sort of made a bumper, and it caused Linda to be diverted farther out into the Pacific Ocean, out into colder water. And you see the reddish orange part there where Linda is 185-mile-an-hour winds, and as it goes westward, you see the energy suck out of the hurricane until it just becomes clouds, a storm, no longer a big major hurricane. Well, I'd like to say in our discussions at that time, thinking worst case scenarios, this, as you can see, is Hurricane Ike. At the time Ike came ashore, this was nonstop houses all the way along here. And when we were looking at Linda with 185-mile-an-hour winds, we were wondering, oh my goodness, is this going to be what Mission Beach looks like if one of those things comes ashore? That was worst case scenario. Didn't happen, but we're just looking at, well, we're talking about big events tonight, so that's about as big as we're going to get them. I thought I'd spend a little bit of time here just going over, this would be Atlantic and Gulf of Mexico hurricane trends. There are several kind of changes of things that are different. One is rapid intensification. It has always been theory and actuality. As a hurricane starts coming into shore, it runs into shallower water with less heat in it, and they tend to slow down in their intensity. But we've been having exactly the opposite with some of them. Do you remember Laura last year? Well, let me define rapid intensification because it does have a definition. It's within a 24-hour period if the rotating wind speeds increase by 35 miles an hour or more. That's rapid intensification. Last year, Laura heading to Louisiana, the predictions had gone out. They were right on about where it would hit, when it would hit, and they said it was a Category 2. However, in that last hour, Laura picked up 65 miles an hour more in wind speed. So instead of a Category 2 hurricane that people didn't think they needed to evacuate from, it came in at a high Category 4, did massive damage. Now here's a little kind of a rule of thumb, if you will. But for every, people have made calculations of this, so that took us as a generalization, an educated estimate. And it's this: when the seawater temperature goes up 2 degrees, that could add 20 miles an hour to the rotating wind speed. So the water temperature is very significant here in terms of what we get in the way of rapid intensification. Another one I'd like to mention here is we've commonly thought about hurricanes as being coastal phenomena. They come in and they slam the coast, and that's where the hurricane does all of its damage, but we're seeing a slower decay. That is to say, if we take Laura, or if we took Ida here from a few months ago, they didn't just dump their energy on the shoreline. They continue on up through the United States with tremendous amounts of rainfall. And what's happening here is when a hurricane comes ashore, it's lost its energy source. The energy that makes a hurricane is fed from the water into the tropical cyclone. When it comes on land, it's cut off from its energy source. But remember, ocean water being warmer now, that means there's actually more moisture held within the storm. And since it has more moisture in the storm, it rains heavy rain for longer distances and longer times inland. Here's another rule of thumb kind of a thing. But basically speaking, if the temperature, the air temperature here, the temperature within the storm is another 2 degrees higher, 2 degrees Fahrenheit higher, it could hold about 7% more moisture. So we're looking at a secondary energy source then. The hurricane comes ashore, cut off from its main energy source, but it has so much energy stored up here within the storm system itself that it can now carry in and do severe flooding, as we've witnessed in the news. Each of the last few years, this sort of thing has occurred. The third thing I want to mention is just calling the slowdown. Is another thing that, here's a little histogram to kind of look at that. Over here on the right side, we're doing the rainfall in inches. And over here, we're looking at the miles of hour, not of the rotating winds, but of the travel speed of the storm. So if it's going 5 miles an hour, like you see on the left side, it might dump 30 inches of rain on a place. If you run your eye over along the bottom to 20 miles an hour, that same storm might only leave 5 inches. And I think the poster child for this phenomenon of the slowdown, which is occurring more commonly, has got to be Hurricane Harvey that hit Houston in 2017. You remember that one? Hurricane Harvey came along and basically just stayed there for 4 days. And you dropped 10 feet of water on Houston, which is flat land, hard for water to drain off. And you remember that? Houston was basically turned into a village, well, a Venice, canals of water around all the buildings. And you remember how difficult that was. So that's another thing here. Some of these hurricanes are traveling slower than they used to, which can mean a lot more rainfall for the places that they slow down or stop over. Hurricane Dorian in the Bahamas, that Category 5 storm stayed for 24 hours on top of 2 of the islands and basically destroyed the buildings there. Let's switch topics now. Let's go back to classic floods. Spent a lot of time on hurricanes here. And again, I'm going to sort of repeat myself here, but what I'm trying to do here is looking for big events. And a hurricane is a big event. The oceans are warming, they're storing more energy. We can see the changes in the hurricanes in the Gulf of Mexico and the Atlantic Ocean. So I'm just trying to bring some of that over to ours and say, what could the next Kathleen or Linda possibly do to us? Now, let's go to the biggest flood probably in California history, 1862. Again, here we are back to the 19th century. And kind of what I'm doing here with these is I'm picking events that have happened to say they could happen again. Do you notice in this global warming or in this increased frequency of severe weather events, we're not talking about necessarily more as much as we're talking about, we're not necessarily talking about more intense or bigger than things you know, but a greater frequency of the big ones that you are familiar with. And for California, the big one would be 1862. There you have within the Sacramento, the San Francisco Bay Area, something like 40 days of nonstop rain, or 40 days in which there was rain. And we're going to talk a little bit more about this, and you're probably up on this because it's in the news a lot here in recent years, and that is atmospheric rivers. We're going to look at that a little bit more. And what apparently happened here in 1862 is just a series of atmospheric rivers, which we're going to look at, hitting from the Columbia River all the way down to San Diego, one after another, coming in at different places, enough to keep most of California under significant amounts of water. Now, here's this arc storm. This is a model made by the U.S. Geological Survey based on those 1862 rainfalls. They've tried to recreate what was the land like at that time. So you look at that word arc storm. The AR is atmospheric river. The little K is for kilo, like 1,000, storm. So the atmospheric river, 1,000-year storm. And look at up the top center there. You see where it's water depth. The deep blue is 10 to 20 feet deep water. Look at the Great Valley. Go to Sacramento up near the top there. And look at that Sacramento area there, that huge, huge area, 10 to 20 feet of water depth for weeks. Look at coming down that whole Great Valley. It's almost like an inland sea at that time. And if we focus down even farther here, just to get onto the Southern California part, well, notice here in the Los Angeles area, notice right in here, they had like 28 days of straight rain there, and the Los Angeles River, the San Gabriel River, the Santa Ana River, they all overflowed, as you can see right there. And for something like 3 weeks, there was an 18-mile across inland sea of water about 4 feet deep. A flood unlike anything, of course, we've seen here in modern times. Now, of course, they don't have the dams at that time. They don't have the cemented in riverbeds and things. I know conditions have changed some since then. But if you had 40 days of rain, of heavy rain, keep coming back and back and back and back, that's going to cause problems no matter what. But let's look a little bit more about atmospheric rivers. And I want to focus here for a moment down on the label down here at the bottom, the Center for Western Weather and Water Extremes. That's out here at Scripps Institution of Oceanography. And their work out there, they're one of the leaders in the world for explaining and understanding of atmospheric rivers. Now you see this particular atmospheric river that's in the illustration there. It's over 1,000 miles long, a few hundred miles wide. It's maybe about 2 miles thick. And the water vapor in there, if we reduce that to being a river, we could say these are the largest rivers on Earth. They are more at their maximum. Some of these have been estimated to have as much water flow in it as water vapor over that broad area you see as 25 Mississippi rivers. So in other words, these are huge rivers of water. There's 3 to 5 around the world at any given time. And what's really significant is you can see the heavy rainfall coming from this particular one where it impinges on Northern California. But what happened in 1862 was a succession of those things coming one after another after another. And I think we've gotten a little bit used to them here from our own weather when we talk about that cute name, the Pineapple Express. So here's one of them. Here's an atmospheric river coming down here from the tropics in near Hawaii, where we have tropical moisture, excess heat. So what's Mother Nature doing with all that excess heat? Transporting it up in this massive atmospheric river and bringing it up into the mid and high latitudes. And then when it hits a place like California, with all its mountains, pushing those clouds up, lifting them up, what they call orographic lifting, pulling that water moisture up into the higher atmosphere, tremendous rainfalls and snowfalls both. And take that Pineapple Express there, with the cute name we use, that's being used by the meteorologist, take that Pineapple Express there, and instead of just having one, which is a few days of rain, have them come in one after another, after another, after another, and that's where we had those severe floods back in 1862 that we were looking at. So the Pineapple Express, the atmospheric rivers, these are things we've experienced. I guess what we're talking about now is, what about when we get several of them that come one right after another? And we do believe that has happened in San Diego. I'm going to work my way up to 1916, the biggest San Diego flood of the 20th century. But I first want to go to this map of San Diego in 1853. So here's San Diego Bay, and we come along. That's the San Diego River there, that black line in the middle. There's the town of San Diego, or Old Town. There's Mission Valley. And as we loop on around this way, this would be the San Diego River Delta. So what are we seeing? If we were here in 1853, here'd be the San Diego River in Mission Valley. We're used to it going straight to the Pacific Ocean, but in 1853, here it goes by the town and down into the bay. And they were having a number of floods there, 1840s and so forth, that was interfering with business. How can the ships come in? How can you do the trading? Population of San Diego at that time is maybe only 700 people, but a lot of their commerce is done via the ocean here. We've got to have boats come in and go out, and with river floods coming into the bay, bringing in silt, changing the shape of the harbor, they wanted to have control. So the U.S. Army Corps of Engineers sent in Lieutenant George Derby. He took several bullets in the legs during the Mexican-American War, where he was underneath the captain at that time, Captain Robert E. Lee, and that pretty much took him out of military action. And West Point graduates are engineers, so he was sent here to build a dike to try to protect San Diego, the town of San Diego, from these floods. In other words, let's make the San Diego River flow directly to the ocean, the way we're used to seeing it today. So here we are with a 1916 flood photo, and I'm just going to color over a little bit right here with a yellow line. Most of Derby's dike got washed out, but basically you're seeing a rebuild of it there, or patch up and rebuild, and you get the idea here. The San Diego River was, as you're looking at this photo, it was taking a left hook and going into San Diego Bay, but by putting the dike there, building that dike, that forced it to go directly on out into the ocean, as we know. Now, if we were looking at what we'd see here today, I mean, there you see the railroad bridge taken out. Well, that's the same place the railroad is today, basically right alongside Interstate 5. And right out here, what you would be looking at today would be SeaWorld, just for orientation here about the views. So January 1916. Now, and going back and looking over the records, and mind you, there's, in terms of understanding the weather, there's just this huge change, you know, pre and post satellite photos, pre and post the time where you actually can see things rather than just isolated rain gauges and wind measurements and such. So we think, or the latest thinking on what happened in January 1916 is one atmospheric river coming in right about the middle of January, and another one coming in at the last week in January. And putting two of those together, well, caused the flood you see here, and we're going to look at a few more photos from 1916. Interestingly enough, in December of 1915, the month before the flood, here's this Charles Hatfield has come to town and said that after years of drought, he could bring rain. He'd make rain if the city council paid him $10,000. Doesn't sound like much today, but in December 1915, $10,000 would be $265,000 today. So Hatfield set up these towers and had fumes and vapors going into the sky right immediately there. So that next month, that was December 1915. The next month, January 1916, in comes 2 atmospheric rivers. So it not only filled Morena Reservoir, which he was contracted to do, filled it to the brim, but it was overflowing. And it wasn't just his fumes. I mean, the rainstorm went all the way up San Bernardino, down to San Diego, down towards Ensenada. It was a massive weather system. A big atmospheric river had come in. But, well, he said he'd fill the reservoir, and he did. But then when he went to go collect his money, they said, well, if you caused that rainfall, that also means that here's the Otay Dam. See the remainder of the Otay Dam right there? That dam burst and broke, opened up. Some eyewitnesses say it was kind of like the opening of gates. The dam split in two and opened, and the reservoir water went as a 40-foot high wall of water down the valley, killing 22 people. And even today, this event, this dam failure, remains the number 6 deadliest dam failure in U.S. history. So it's a very significant event. So the city council said, well, we'll pay you your fee, but then you also are going to take care of the lawsuits for the damages and all that your rain caused. So basically Hatfield retired, went into the sewing machine business, and wasn't really heard from again until 1957 when they made that movie, The Rainmaker, with Burt Lancaster and Katharine Hepburn. The movie got nominated for Oscars. It wasn't this story exactly, but it was an adaptation of the Hatfield story. So that's kind of its mark in history, if you will. But here's the Sweetwater Dam. The whole dam didn't fail, but you can see it's not doing what it's supposed to. That wasn't supposed to be a spillway there. And here we are back again at Old Town at the bridge over the San Diego River that was taken out. And when you look at the water flow, they say that the water was flowing in Upper Mission Valley. We're down here, you recognize, we're looking basically over at Old Town here. They say that the water flowed from wall to wall in Mission Valley. They sent ships sailing up Mission Valley to right where San Diego State University is building a football stadium now, picking people off of rooftops and out of trees, rescuing them from these floodwaters. So that's really the biggest flood we've had in the 20th century. Haven't done much here in the 21st century yet. But again, what has happened can happen again, and here's one aspect of this. We now have dams. In this image, a bunch of images put together by Phil Constantine, you see San Vicente Dam, the reservoir, a lot of storage capacity there. But of course, floodwaters will fill up a dam. And then there comes that question, the dam there, if we look at it from below, does that dam do much to prevent floods if the reservoir is full? And the actual answer is kind of surprising. It actually does. It's kind of like people feeding into the gate at a stadium. They're all there, but they can't all go in at the same time. So you can fill up the reservoir, but with the dam there, all the water can't go out at once, and therefore the dam still does some help. I want to go a little bit more with this. Here's a flood plain, and basically the flood plain is the river bottom. It's the bottom of the river during floods. And basically the river builds the flood plain, and it reserves the right to reoccupy it whenever it sees so fit. So let's look at this particular general diagram here and say, let's say this is Mission Valley. Say this is Interstate 8 running right down along here, and saying all of Mission Valley then is basically the river bottom during floods. So all the buildings and all we've built have been built in the flood plain. Now, it's kind of an interesting, I guess, political history of San Diego of what they have done for flood control in Mission Valley. Let's look way to the left there. 115,000 cubic feet per second. Oh, by the way, let's orient ourselves a little better here. Here's Interstate 8 coming out of Mission Valley to Ocean Beach, and then here's Old Town, Interstate 5 going along Mission Bay. So that's the big flood control channel. The 1916 flood, they say, was 72,000 cubic feet per second. So this is the 1940s, Land's not so valuable then, population's not overwhelming then, so we're allowed to build a really big flood control channel, as you see there. It could handle a flood bigger than 1916. Well, we move on to building of the Town and Country Hotel and Fashion Valley and those kinds of folks who land is very valuable to them. So we see the capacity of the channel there, 8,000 cubic feet per second. Well, basically nothing was done, what it boils down to. And then the third segment over here between Highway 163, Interstate 805, is designed to handle 49,000 cubic feet per second. Well, the numbers are not things I'm wanting you to memorize or anything, but I'm just trying to say is one flood. Well, visualize 1916. If 72,000 cubic feet per second came down into a 49,000 foot channel, they're overflowing. They hit the 8,000 one, that's pandemonium. They hit the ones west of Interstate 5, and it's nicely contained. As you can see, it's very uncoordinated, or should I say virtually a total lack of planning here in San Diego. Now let me just look at a photo here. So here we are, we're looking at the freeway interchange. You see there's Interstate 8 and Interstate 5. So the view here is up Mission Valley. So I want you to notice here the flood control channel, the 115,000 cubic feet per second one. That's the one you drive on Interstate 8 when you're heading on into Ocean Beach. Big, wide floodplain. The other one, if we take the little arrow up above, we see, well, there's on the left of the arrow is Fashion Valley. On the right, get to Town and Country. And, well, that's not much of a flood control channel. And here's a photo from February 1980 floods. Now we're looking the opposite direction. We're looking out to the Pacific Ocean. So look up to the top there and see there's the flood control channel there. Water from wall to wall, nicely contained in the flood control channel. Golf course flooded, that's no problem. Golf courses are actually good things to build on floodplains. Golfers like hazards anyway. And then we come over here to Fashion Valley and Town and Country Hotel, and then we see how wide it is out there and how wide it is here. Well, that lower arrow right there, that, pointing right on the tips on Fashion Valley Road, I went there yesterday and snapped a photo looking east to see what does this flood channel look like today. There it is. That's the heart of the flood channel at Fashion Valley Road. You can field check me. Just drive Fashion Valley Road in there and look for the San Diego River. You're not going to see much. I walked about 1,000 feet up. There was a little pedestrian bridge that goes across there, and that's the San Diego River going back up towards the buildings there in Mission Valley. So, well, let's just say if we do get some big floods, not all parts of the city are as well prepared as they might be. This is hurricane stuff, but what I wanted to do here is look at three different things to kind of understand where we are these days. Now, in hurricanes, there used to be the three big killers: the storm surge, the water pushed ashore by the hurricane, the wind, and then inland flooding. And the storm surge, well, Bangladesh in 1970 had a cyclone come ashore that killed an estimated 300,000 people. That's 1970. These days, look at for the U.S., storm surge, about 12% of the deaths, wind, about 12%, and this is mainly due to the fact that we get good warnings now. It's not a shock or surprise when a hurricane comes. There's a lot of folks, of course, who will never evacuate or anything because it couldn't happen to them, and I've been through a hurricane before, so I'm not worried about it. But where are the deaths now? Inland flooding. We were talking about Laura, Ida, ones going farther inland and dropping all their rain. That's the flooding there. I'm talking about, I'm using that hurricane death ones there because that's a little table that shows the difference. So for hurricanes, the flooding now is the biggest aspect. And of course, that's what we'll be most concerned about if a tropical storm comes ashore here in San Diego. And this inland flooding, for the most part, it's people, it's almost like 2/3 of them are people in cars. And by and large, it's not people who are driving along a road who are innocently swept off by a flood. It was people driving across things like this. Here's Mission Center Road going across the San Diego River here in 2010. And, well, you know how life is these days. I mean, you drive over that Mission Center Road all the time and you're in a hurry. You got something important you got to do on the other side, and you slow down and you stop and you think, that water's not that deep. I can drive through that. And then, well, can you? Look at the top diagram there, where the water 1 foot deep has 500 pounds of lateral force. And when you look at that car, you're sitting in a big heavy car, something probably a lot heavier than is drawn there in this diagram. But what's actually in contact with the ground? The bottom of 4 tires. You don't have much of that weight firmly supported. Drop down to the one below. Let's say the water's 2 feet deep. That's 1,000 pounds of lateral force. And if the water comes up higher than the base of the car, you get the buoyancy. You get an uplifting force to take that car and move it. And so the advice very simply is, if you find yourself in that situation about there's a road you're familiar with and you think you can get across it, I think that saying's become kind of famous right now, but I hope so. Turn around, don't drown. The water is far more powerful than you realize, or not you, but that some people realize. One last concept I'd like to go through here is the effect of urbanization on flood frequency and water elevation. Big fancy titles, but let's look here a little bit. Here's just a generalized diagram I drew, and all I'm talking about here is on the vertical axis over here, increasing rainfall. The horizontal axis, we're looking at time in days. And so by the green, this little histogram is supposed to represent a volume of rainfall, and then the rain runs off the ground, what they call the rising limb of the flood, and then the falling limb. And it's asymmetrical. You know, more of the water runs off fast, and then some goes underground. It keeps flowing little by little into the river over time. Now, this is me drawing just a generalized drawing. Let's look at one that's an actual plot of real data. Now, this is from Buffalo Bayou in Houston, Texas. And what they did here, you notice there's a date here of, on one of these of October 6, 1949, and over here, one in June 1960. And they were selected because these were basically identical rainfalls, same amount of rainfall for the same amount of time. So what we want to look at is the runoff. What's the shape of the runoff curve? Now, on that horizontal axis there, where we're doing it's in hours, so there's 1 day, 2 days, 3 days, so we're basically looking at about 4 days. So what happens here in the rural? Rain runs off of the surface, a lot of it soaks into the grounds, held back by vegetation, and it slowly feeds into Buffalo Bayou. Now today in Houston, if you've been there, there's not a whole lot of open land in Houston anymore. And so what does the rain fall on now? It falls on the roofs of houses, it falls on streets and sidewalks, it falls on parking lots, it falls on ground that's covered over. It's impervious. Water can't soak into it, so what can it do? It has to run off. And look at this runoff curve now. Look how the curve has changed. Look at how rapid the flood occurs, at how high it is, and then the good news is it's over faster. Now these are real numbers. So when you look at this, the rural one here, where it's a little over a 1,000, the units don't matter, but 1,000 cubic feet per second, then up here it's over 4,000. So basically the same rainstorm, you get a 4 times higher flood crest in a paved urban city than you did when it was farmland. So that's an important principle that I don't think cities in general have paid enough attention to, namely allowing enough ground around to absorb rain. It's not just a matter of building cement. Every bit of cement you put down makes the water run off faster, and if it's a lot of rain, it not only runs off, it does run off faster, but it runs off way higher. And of course, that's the real problem, flood heights. One last little thing, I just thought we'd take a look at the Tijuana River. So here we are, we're looking across the border. There I just kind of drew in the border a little bit. And in Mexico, you see a big cement-lined channel carrying the Tijuana River. The U.S. was supposed to build a concrete channel also, but then our ideas changed and we wanted more of the environment, so we have left it open as floodplain. So you can see then that that water that comes out of that cement channel in Tijuana just spreads out over the floodplains in the U.S. And on the left side there, that's Interstate 5. So anyway, you kind of see, I just show it just as another way of understanding flood runoff or floods in the San Diego area. So we'll stop here with this overwhelming flood, one of my favorite waterfalls. That's Dettifoss in Iceland. And I thank you very much for your interest. And if there are any questions, I'd be happy to answer them. Well, this year, from Kimberly, are we experiencing La Niña or El Niño this year? So far, we're having a relatively mild La Niña so far. And I was focusing on El Niños, which were, with its heat, we usually associate big El Niños with a lot of rainfall for us. Well, La Niñas, we typically would have less rainfall. And the bad news for the U.S. on La Niñas is the winds are such that it promotes hurricane development. El Niño tends to discourage wind movement, or hurricane formation, sorry. I don't know if you will, way back that one diagram I had where the winds were blowing the waters across the Atlantic Ocean. I said the hurricanes are growing as they cross the ocean. That's accelerated in La Niña times. In El Niños, when the winds are blowing back the other way, storms are coming from Africa and the winds are blowing back this way, they tend to destroy them. So mild La Niña, we wouldn't expect big rainfall from this, but there's no guarantees. Mother Nature will do as she pleases. We just write it down and average it out. From Claudia, is there a prediction of a possible hurricane in San Diego based on the hurricanes developed down in Baja California if waters continue to heat up? That's a good thing to bring up is discussing Baja California. The Los Cabos region has become so popular as a tourist destination. I'm sure many of you have been there. But they rather routinely are hit by severe hurricanes there. We were looking at that East Pacific warm pool of water, seeing how many hurricanes develop there, and then how many of them develop that Coriolis right hook and cross the Baja California Peninsula. So I don't think we'd ever get as many as they do down there because the water down there is warm almost all the time. But effectively what I was doing or sort of entertaining the idea of is that East Pacific warm pool, as that warmer water moves, or more water is warmed farther north, means more hurricanes would have a chance to travel farther north, and that means it would increase the frequency of them for San Diego. And again, this is like big earthquakes. They're not saying one's coming tomorrow or anything like that. We're looking over the longer time span and saying, how might things change? If it took it for the whole 21st century, then I think the odds would be pretty darn good of a hurricane hitting San Diego. But on a more short time scale, I don't know. From Charles, what indicator could we use to anticipate a severe storm? Water temperature, air temperature, low pressure in the Pacific, basically all those kinds of things. And again, for a severe storm, if we're talking about the atmospheric rivers, well, we're doubly fortunate to have one of the world's leading research institutes on atmospheric rivers right here in town. So I would hope that means we'd get an even earlier look at it, or looking at basically our own local area. But that is a good thing these days with the satellites, with the improving computer models. If I'm talking about hurricane placements, the computer systems now are quite good. Where a hurricane used to make landfall, they used to say, well, somewhere along this 100-mile stretch of coast, they're getting some of those things down now to within a half a mile or so of where they come ashore. My point being that prediction is really making great strides on some aspects of these, and the models then basically, in building a model, you're trying to do all kinds of things like water temperature, air temperature, all those sorts of factors, putting them together to try to model how they interact. In other words, I'm not going to say predict, but say forecast what might be coming for us. Do you know if the city of San Diego has plans to improve flood control through Fashion Valley? I'm not up on plans, so I don't know. We don't see much action, and I was trying to show for the 3 different time intervals that flood control was built there. Frankly, those diagrams are from my textbook. I put it in the textbook because I thought it was a world-class example of how not to do things, to have 3 totally misconnected flood control channels. From Tony, there are a number of large complexes of condos going up in Mission Valley. What can we expect of floods in this area in the future? Do you know of how planning has addressed this? Well, FEMA, the Federal Emergency Management Agency, they have made up a lot of standards. They focus a lot on what they call the 100-year flood. The flood, when you plot flood frequencies or flood sizes over years, you get kind of a frequency curve of what size floods occur at what times. So they've been pretty firm about not building below the 100-year flood level. Now, when you get down to individual projects, I don't know exactly, you wouldn't have to go and look and see exactly what constraints were put on them. But it's the usual kind of a thing where the developer sees very valuable land and wants to use it, and then a flood control person is saying, no, we need that land for floods. And then their other response is, what floods? This is San Diego, we don't get floods. So you get that tug of war going back and forth. And I'm really not up on that part about what is being done. Okay, well, again, I thank you for your interest on big floods, and I hope you're back next time for our big wildfires one. I think we've got a lot of interesting things to talk about there again. Thank you for your interest.